Somewhere in our galaxy tonight, the dead core of a star is sitting in the dark about 12 miles across, weighing more than our Sun. Its surface is harder than diamond. Its gravity is 200 billion times stronger than Earth's. And at its very center, the matter we know how to describe ends. The neutrons that give the object its name break down. The boundaries between particles dissolve. What sits there inside may be something that does not exist anywhere else in the universe, a cold, dense ocean of free quarks, held together by gravity behaving in ways that no laboratory on our planet has ever been able to reproduce or test. In late 2023, a team in Finland used a supercomputer to work out with as much rigor as the science currently allows that the largest neutron stars almost certainly contain this strange matter at their hearts. Not as speculation, as the most likely answer. Tonight, we are going to drift down through every layer of one of these dead stars, from the iron crust at the surface to the impossible matter at the very bottom. If you find yourself drifting off to these quiet cosmic mysteries, hit like and subscribe to Cosmic Drift. Now, let us drift inward through the dark toward the center of a dead star. Imagine standing some safe distance from one. The neutron star itself is small, the size of a small city, a sphere of dark, smooth, silent material that does not glow much in visible light. If you could see it from a few hundred miles out, what you would notice first is not the object itself. You would notice what the object's gravity does to the space around it. Light from distant stars bends as it passes nearby, smearing into rings and arcs. Time near the surface runs more slowly than time where you are floating. If you dropped any ordinary object toward the surface, it would fall with such speed that long before it landed, it would be torn into atoms, and those atoms would be torn into nuclei and electrons, and those nuclei and electrons would be pressed into the surface so violently that they would simply become part of the star. There is no soft landing on a neutron star. There is no landing at all in any human sense. The object you would be looking at from your safe distance is the place where matter and gravity have reached an arrangement that nothing in your everyday experience prepares you to understand. Now imagine going inside, not literally. Nothing alive could survive even within 1,000 miles of the surface, but in your mind follow the matter inward. Pass through the thin atmosphere of plasma. Pass into the solid crust made of iron and heavier metals arranged in a crystal lattice 10 billion times stronger than steel. Keep going. The density rises. Past a certain depth, neutrons begin to leak out of the nuclei and roam between them as a free fluid. Deeper still, the nuclei dissolve entirely, and there is nothing left but a sea of neutrons with a small fraction of protons and electrons mixed in all of it, behaving as a quantum fluid. Colder in the relevant physical sense than the liquid helium in any cryogenic laboratory on Earth. Keep going, deeper. The pressure rises until it is roughly more than anything that could ever be created in a controlled experiment. And here, in the deepest part of the star, the matter does the thing this whole drift is going to be about. It changes, not chemically, not into a different kind of atom, into something that by every classical description we have should not be able to exist as a stable, persistent, gravitationally held form. The neutrons stop being neutrons. The strong force that normally locks quarks inside their host particles loses its grip, and the quarks become free to wander through the medium as a continuous quark fluid. A new state of matter hidden inside the dark heart of a dead star, sitting there for tens of millions of years, never observed directly, never brought to a laboratory, never reproduced on Earth. Until late 2023, when a team of physicists in Finland produced the strongest evidence yet that this material really is there in the cores of the most massive neutron stars behaving the way the equations have always predicted it could. That is what we are going to walk down toward tonight, slowly, layer by layer, with all the time you need to let each new piece of the picture settle. There is no rush. The matter inside a neutron star has been there for as long as the star has existed, in some cases tens or hundreds of millions of years, and it will continue to be there for a long time after we have finished our slow drift. The story does not require any speed from you. It only requires a little patience and a little curiosity, both of which you have already demonstrated by being here listening to a voice describe one of the strangest objects the universe has ever assembled. Before we go inside, I want to give you the basic picture of what a neutron star actually is and how we know they exist at all. Because the road to understanding these objects is one of the more remarkable stories in 20th century physics. The objects were predicted theoretically decades before any of them were ever found by physicists who had only the loosest sense of how matter behaves at the edge of what gravity can produce. The story begins in a sense in 1932, when an English physicist named James Chadwick, working at the Cavendish Laboratory in Cambridge, announced the discovery of a new subatomic particle. He called it the neutron. It was, he showed, an electrically neutral particle of roughly the same mass as the proton sitting alongside protons inside the nuclei of atoms, contributing to the nucleus mass without affecting its charge. The discovery completed in broad strokes the picture of atomic structure that physicists had been piecing together since the late 19th century. Atoms had nuclei contained protons, and neutrons, electrons, orbited the nucleus at relatively enormous distances. Chadwick's neutron was the missing piece. He won the Nobel Prize for it 3 years later. What is striking about the next part of the story is how quickly theoretical physicists ran with the implications. Within 2 years of the neutron's discovery in 1934, 2 astronomers working at Mount Wilson Observatory in California, a German named Walter Baade and a Swiss-American named Fritz Zwicky, published a paper that proposed something audacious. They suggested that when a massive star runs out of nuclear fuel and dies, its core might collapse so violently that it would no longer be made of ordinary atoms at all. Instead, the core might be compressed so completely that the protons and electrons would merge with each other, leaving behind a body composed almost entirely of neutrons. They coined the term neutron-star for this hypothetical object. They predicted in the same paper that such collapses would be visible from Earth as the brightest kinds of stellar explosions, which they called supernovae. The idea was speculative. The math was rough. There was no way with the instruments of the 1930s to test whether any such object actually existed. A few years later, in 1939, 2 American physicists, J. Robert Oppenheimer and his student George Volkoff, working at the University of California at Berkeley, took the idea further. They wrote down a more careful theoretical equation for what such a neutron-rich body would look like, building on earlier work by another colleague named Richard Tolman. Their calculation, now known as the Tolman-Oppenheimer-Volkoff equation, established that there was a maximum mass above which such a body would collapse further into something even denser, something that we now call a black hole. Below that maximum mass, an arrangement of pure neutrons supported by quantum mechanical pressure could in principle exist. But above it, no force in the universe could hold the matter up against its own gravity. The equation set a limit. It said, "This is the heaviest thing nature can make, and still call it a star." That paper was published in October of 1939. It is sometimes pointed out that the Oppenheimer-Volkoff calculation appeared in the same journal issue alongside Albert Einstein's paper, arguing that black holes could not actually form in the real universe. Einstein turned out to be wrong about that. Oppenheimer and Volkoff turned out to be right more or less about the theoretical existence of neutron stars and the upper mass limit. But for the next 30 years, neither prediction had any direct observational support. Neutron stars were a theoretical possibility sitting in the literature waiting for someone to find one. The wait ended in 1967 when a young graduate student at the University of Cambridge named Jocelyn Bell Burnell noticed something strange in the data from a radio telescope she had helped build. We will come back to that discovery in a few minutes. For now, what matters is that her finding, eventually understood as the first detection of a neutron star, vindicated the long theoretical prediction. Barde and Zwicky's neutron stars were real. They were out there in the galaxy in numbers that astronomers now estimate to be on the order of 1 billion. Most of them are quiet and undetectable. Some, the rotating ones whose magnetic fields sweep beams of radiation across the sky, blink at us regularly enough to be timed to fractions of a microsecond. Others, the most extreme, distort space-time around them in ways we can measure with gravitational wave detectors. The theoretical objects Chandrasekhar and Oppenheimer and Volkoff and Barde and Zwicky and many others had worked out on chalkboards in the 1930s turned out to be a real and abundant feature of our galaxy. Before we walk into one, I want to give you the layered structure in rough outline so you can hold it in your mind as we descend. Each layer will get its own treatment in the body of this drift, but it helps to see the whole shape first. At the very outside, a neutron star has a thin atmosphere of plasma, only a few centimeters to a few meters thick. This atmosphere is so thin and so hot that it is essentially a layer of stripped bare atomic nuclei and free electrons held against the surface by gravity. Below the atmosphere, the surface itself is a solid crust perhaps a kilometer thick, made of iron and heavier metals locked into a crystalline lattice. Below the crust, things start to get strange. The density rises so quickly with depth that the nuclei become more and more neutron-rich, until at a depth of perhaps half a kilometer below the surface, the nuclei become so neutron-saturated that some of the neutrons begin to drip out and form a free fluid between the nuclei. This is called the neutron drip line, and below it, you have a region that is partly a lattice of nuclei and partly a sea of free neutrons swimming around them. Go a little deeper, and the nuclei dissolve completely. Now you have a fluid of neutrons with about 10% or so as protons and an equal number of electrons to keep the charge neutral. This is the outer core. It is a quantum fluid behaving in some ways like a superfluid, with bizarre properties at the scale of the whole star. Vortex lines run through it. The protons may form a superconductor. The electrons fly through the lattice as a degenerate gas. None of this resembles any kind of matter you encounter in daily life. And then at the very deepest part of the most massive neutron stars comes the layer this whole script is really about. The pressure becomes so high that even the neutrons themselves cannot survive as discrete particles. The boundaries between them break down. The quarks inside, normally locked tight by the strong nuclear force, become free to flow as a continuous medium. We call this deconfined quark matter. It is theoretically predicted by quantum chromodynamics, the part of physics that governs the strong force, but it has never been seen in any laboratory in a stable form. The closest we have come is recreating it briefly at extremely high temperatures in particle colliders. Inside a neutron star, the conditions are different. The quark matter, if it exists, is cold by particle physics standards and stable and gravitationally confined. It sits there possibly for the entire lifetime of the star, doing whatever quark-matter does, while the rest of the universe spins on around it. That is the layered structure in rough outline. An atmosphere, a solid crust, an inner crust where the nuclei begin to drip neutrons, an outer core of mostly neutron fluid, and a deep inner core where the matter may have made the final transition into a state we cannot reproduce. We are going to walk down through every one of these layers slowly. We are going to talk about how each one was figured out, what the matter is doing in each one, and what we know and do not know about how it all fits together. By the time we are done, you will have a complete tour of one of the strangest objects the universe contains, from the outermost atmosphere to the deepest impossibility at the center. But first, the discovery story. Because the path from Baade and Zwicky's 1934 prediction to the modern understanding of these objects has its own quiet drama. It involves a graduate student in Cambridge in the 1960s, a set of regular radio pulses that nobody could initially explain, and an in-joke about little green men that almost ended up in the literature. That is where we are going next. The story of how the first neutron star came to be discovered is, in its own quiet way, one of the better stories in 20th century physics. It involves a graduate student who built her own radio telescope by hand, a set of regular pulses that nobody could initially explain, and a deliberately silly placeholder name that nearly ended up in the literature. The discoverer was a young Northern Irish researcher named Jocelyn Bell Burnell, who at the time of the discovery in 1967 was working on her doctoral thesis at the University of Cambridge under the supervision of an astronomer named Anthony Hewish. The telescope she had spent 2 years helping build was an array of wooden posts and copper wire spread across about 4.5 acres of farmland outside Cambridge, designed to detect rapid fluctuations in radio signals coming from the most distant parts of the universe. Bell Burnell's job was to analyze the chart paper output of the telescope by hand. The instrument produced about 96 feet of paper recording per day, and Bell Burnell, by her own later account, taught herself to recognize the various kinds of signal that showed up in the data. Most of what she saw was either real astronomical sources, like the bright distant galaxies known as quasars that the telescope had been built to study, or ordinary terrestrial interference like sparking electric fences and bursts of radio noise from passing cars. Distinguishing between the real and the spurious was a craft she developed over her first months on the project. She was, by the time the discovery came, very good at it. In late 1967, she noticed something on the paper output that did not fit either category. It was a regular pulse of radio energy, very faint, repeating once every 1.3 seconds, with a rhythm so steady it was almost like a metronome. The pulse appeared in roughly the same patch of sky each time the telescope swept past that direction. It was not interference because it tracked the celestial motion correctly. It was not a known kind of astronomical source because nothing the team had ever heard of pulsed at such a regular mechanical seeming pace. Bell Burnell brought the data to her supervisor. Hewish was initially skeptical that the signal was real. He suspected an instrumental artifact, perhaps something in the telescope's electronics, perhaps human-made interference reflecting off the moon. They built additional equipment to rule out the artifact possibilities. The signal stayed. For a few weeks, the team did not know what to call the source. It was clearly real, clearly astronomical, and clearly unlike anything ever observed before. The pulses were so regular and so artificial seeming that, as a kind of joke, the team labeled the source LGM-1 for Little Green Men 1. The label was internal. Nobody on the team genuinely thought the signal was from an alien civilization, but it captured the strangeness of what they were looking at in a way that more cautious astronomical labels did not. The pulses were frankly weird. A few weeks later, Burnell found a second pulsing source in a different part of the sky with a slightly different period, then a third, then a fourth. Whatever was producing these signals, it was a class of object, not a single anomaly. And no civilization, however widespread, would announce itself by setting up identical metronomes at 4 widely separated points in the galaxy. The little green men hypothesis collapsed under the weight of the second source. The signals had to be natural. Within months, theoretical astrophysicists around the world began converging on the explanation. The pulses were coming from rotating neutron stars. A neutron star predicted by Bade and Zwicky in 1934 and worked out in more detail by Oppenheimer and Volkoff in 1939 would be tiny and dense, perhaps 12 miles across. If it had a strong magnetic field, the field would be tilted relative to the rotation axis, the way the Earth's magnetic field is tilted relative to the geographic poles. As the neutron star rotated, the magnetic poles would sweep around through the surrounding space, and any beam of radiation emerging from those poles would sweep across the sky like the beam of a lighthouse. If Earth happened to lie along the path of one of those beams, an observer here would see the beam pass once per rotation of the star. Pulse dark with a period set by the spin rate of the underlying object. The fact that the pulses came every 1 1/3 seconds in the case of Burnell's first source meant the underlying object was rotating once every 1 1/3 seconds. For a sphere only 12 miles across, that meant a rotational speed faster than anything anyone had ever directly observed in nature. For a sphere with the mass of the Sun, that meant a rotational kinetic energy enormous enough to power the radio emission at exactly the brightness observed. The picture fit, the numbers worked, and by 1968, the consensus had formed. Pulsars were spinning neutron stars. The theoretical predictions of the 1930s had finally found their observational targets. Burnell's role in this discovery is one of the more discussed historical episodes in modern astronomy. When the Nobel Prize in Physics was awarded in 1974 for the discovery of pulsars, it went to Anthony Hewish and to Martin Ryle, the head of the Cambridge Group. Burnell was not included. Many physicists then and since considered this an injustice, given that Burnell was the one who had actually noticed the signal in the data and pushed for it to be taken seriously. Burnell herself has spoken about the episode many times over the decades, generally, with a great deal of grace, sometimes pointing out that graduate students at the time were rarely included in Nobel decisions, sometimes acknowledging that she would have preferred to be included. She has gone on to a long and distinguished career in astrophysics. She was made a dame in 2007. In 2018, she received the Special Breakthrough Prize in Fundamental Physics and an award worth $3 million, which she immediately donated to fund scholarships for women minorities and refugees pursuing physics research. Her name today is on dozens of awards and prizes, and her place in the history of pulsar discovery is universally acknowledged, even if the 1974 Nobel itself is still occasionally argued about. Once pulsars were understood as rotating neutron stars, the floodgates opened. Astronomers found more of them. Hundreds, then thousands. Some pulsed every few seconds, some every fraction of a second, and a few, the so-called millisecond pulsars, pulsed hundreds of times per second. The fastest known pulsar today, an object designated PSR J0740+6620, located in a globular cluster called Terzen 5, rotates 716 times per second. Its equator, accounting for the size of the neutron star and the speed of its rotation, is moving at roughly a quarter the speed of light. A neutron star spinning that quickly is by any standard near the physical limit of what the matter inside can withstand. Faster than that, and centrifugal forces would tear the star apart. Other neutron stars revealed themselves through different signatures. Some are detected through their X-ray emission, particularly in binary systems, where the neutron star is pulling matter off a companion star, and that matter is heating up violently as it falls onto the surface. Some are detected through their thermal emission, the slowly cooling glow of stars that, while no longer producing nuclear fusion, are still hot enough from their formation to radiate weakly across various wavelengths. A specific subclass called magnetars have magnetic fields up to 1,000 trillion times stronger than Earth's, and they produce occasional bursts of soft gamma-ray flares so intense that an event in 2004 from a magnetar called SGR 180620 affected the Earth's atmosphere from 50,000 light-years away. Each new detection method has expanded our census of these objects, and our current understanding is that there are roughly 1 billion neutron stars in our galaxy, the dead cause of essentially every massive star that has ever lived and gone supernova in the Milky Way's long history. One of the more historically interesting neutron stars is the Crab pulsar sitting at the center of the Crab Nebula in the constellation Taurus. The Crab Nebula is the expanding debris cloud of a supernova that was observed by Chinese astronomers in the year 1054, who recorded a guest star that became for a few weeks bright enough to be visible during the day. For 900 years, the nebula was understood as the remnant of that ancient supernova, but the central object was a mystery. In 1968, just months after Burnell's announcement of pulsars, astronomers in Arizona detected a pulsing radio source at the heart of the Crab. The source pulsed 30 times per second. It was a neutron star, the dead core left behind by the 1054 explosion, still spinning rapidly, almost a millennium later, sending its lighthouse beam across the galaxy with each rotation. The Crab pulsar gave physicists an object whose age they knew with unusual confidence. They could compare it to other pulsars and trace the long, slow process by which a young, rapidly spinning neutron star gradually loses rotational energy, slows down over millions of years, and eventually goes quiet. Younger pulsars, the Crab pulsar, showed spin faster. Older ones spin slower. The whole population of observed pulsars fits into a long arc of cosmic aging, from the millisecond rapid spinners of the youngest neutron stars to the multi-second slow turners of the oldest still detectable ones. The most dramatic single moment in modern neutron star observation came in August of 2017. The Laser Interferometer Gravitational Wave Observatory, known by its acronym LIGO, with its European partner Virgo, detected a gravitational wave signal that lasted about 100 seconds and ended with a sharp peak. The signal came from a direction that was rapidly localized to a small patch of the southern sky in a galaxy called NGC 4993, about 130 million light-years away. Within hours, optical telescopes around the world swung to that patch of sky and found a new bright point of light that had not been there a few days earlier. The point of light was a kilonova, the visible glow of a vast cloud of newly synthesized heavy elements thrown off by the collision of two neutron stars. This event, designated GW1708-17, was the first time gravitational wave astronomy and traditional electromagnetic astronomy had ever observed the same single event together. The combination produced a wealth of physics. The duration and shape of the gravitational wave signal told us about the masses and sizes of the colliding objects. The kilonova spectrum observed across radio-infrared, optical and X-ray wavelengths over the following weeks and months told us about the heavy elements being synthesized in the debris cloud. By comparing the gravitational wave arrival time to the gamma-ray arrival time, physicists confirmed that gravitational waves travel at the speed of light to a precision better than 1 part in 10 to the 15th. Astronomers measured the rate of expansion of the universe by an entirely new method. Most importantly for our story, the kilonova confirmed something that had been suspected for decades but never clearly demonstrated, that neutron-star mergers are one of the main factories in the universe for producing heavy elements. The gold and platinum and uranium and other elements heavier than iron, it now seems, are largely manufactured in events exactly like this one. Kilonovae scatter these elements across surrounding space, where they eventually find their way into new generations of stars and planets and eventually living bodies. The J0740+6620 signal also told us indirectly about the equation of state of neutron-star matter. The way the two stars deformed each other in the final seconds before merger, called tidal deformability, depends on how compressible the matter inside each star is. A stiffer equation of state produces less deformation and a different gravitational wave signature than a softer one. The 2017 signal favored equations of state on the stiffer side, which fits with what is needed to support the observed 2 solar mass pulsars. Every subsequent neutron-star merger detection, of which there have now been a small number, has added more constraints. The Helsinki paper we will get to shortly used these constraints among others to arrive at its final result. There is a quiet thread to pull on here, which we will pull on more fully in the resolution of this drift. Some of the heavy elements in your body, in your wedding ring, if you have one, in the iron in your blood, in the trace metals in every cell, were produced in events much like the GW1770817 merger billions of years ago in earlier neutron-star collisions in the proto-Milky Way. The dead stars whose cores we are descending into tonight are not just curiosities. They are part of the story of where you came from. But before we get to that part of the story, we need to actually walk into one of these objects. Now that we have established what they are, where they are, and how they were found, we can start the descent. Begin at the surface with the atmosphere and the solid crust. The first kilometer of a neutron star before the neutrons begin to drip, and the matter starts to behave in ways that have no familiar analog. The crust, with its iron lattice 10 billion times stronger than steel, with its starquakes and its strange shapes deep down where the nuclei begin to deform. That is where we go next. The first thing you would encounter descending toward a neutron star from above is the atmosphere. The word atmosphere is being used loosely here because what sits on top of a neutron star bears almost no resemblance to the air around our planet. It is a thin layer of plasma, only a few centimeters to perhaps a few meters thick, depending on the star's age and temperature. The plasma consists of stripped bare atomic nuclei, mostly hydrogen and helium, left over from accretion off a companion star, along with the electrons that have been peeled away from those nuclei by the heat. There is no breathable air. There is no oxygen, no nitrogen, nothing recognizable as gas in any everyday sense. There is just a hot ionized soup held against the surface by gravity so strong that the entire atmosphere is squeezed into a layer thinner than the thickness of a human body. The temperature of this plasma can range from about 1,000,000 degrees in older neutron stars to tens or hundreds of millions of degrees in the youngest ones freshly formed from supernovae and still cooling off. The plasma emits thermal radiation in the X-ray band, which is one of the ways modern astronomers detect and characterize individual neutron stars. The neutron star interior composition. Explorer, an X-ray telescope mounted on the International Space Station and known by its acronym NICER, has been measuring this thermal emission for years now, using it to constrain the radii of nearby pulsars to within fractions of a kilometer. Those measurements feed directly into the broader effort to understand what kind of matter is sitting underneath the atmosphere in the crust and below. Drop through the atmosphere in your imagination and you arrive at the surface. The surface of a neutron star is a solid, not a liquid, not a gas, not anything in between. It is a crystalline crust made of iron and heavier metals locked into a rigid lattice. The strength of this crust is one of the more striking facts about neutron stars. Calculations and computer simulations published over the last decade have shown that the iron lattice of a neutron star crust is by some measures 10 billion times stronger than steel. It is, as far as we know, the strongest known material in the universe. Stronger than any alloy that human metallurgy has ever produced, stronger than any natural mineral on Earth, stronger than the diamond lattice. And it has to be that strong because it is holding back the gravitational pressure of the entire interior of the star, which is constantly trying to compress the surface inward. The crust itself is perhaps a kilometer thick, give or take, depending on the mass and age of the star. It is structured in layers. The very top of the crust is iron, similar in composition to the iron core of an Earth-like planet, but compressed to a density that no terrestrial sample of iron has ever experienced. As you descend through the crust, the density rises. The iron nuclei become surrounded by an ever denser sea of electrons, which are degenerate, meaning they are filling all available quantum states from the lowest energies up the same physical condition that supports white dwarf stars against their own gravity. The electrons exert their degeneracy pressure outward, and the pressure rises with depth as more and more of the available quantum states are filled. Inside this dense electron sea, the iron nuclei are still discrete. They sit in a crystalline arrangement, vibrating slightly, but mostly stable, locked into a lattice, the way atoms are locked into the crystals of any solid material on Earth. What is different is the gap between the lattice sites and the strength of the forces holding them together. In a piece of ordinary iron at room temperature, the atoms are separated by gaps that are filled with electronic orbitals and chemical bonds. In a neutron star crust, the gaps are similar in absolute size, but the electrons between the nuclei are no longer organized into chemical orbitals. They are a degenerate gas free to flow through the lattice, providing pressure, but not the kind of chemistry we are used to. The result is a solid that is rigid dense and behaving in ways that no piece of ordinary iron ever does. Go deeper into the crust and the nuclei themselves begin to change. Under the rising pressure, energetics start to favor nuclei with more neutrons and fewer protons, because the available electron sea can absorb the extra electrons that would otherwise have to balance the proton's charge. So the nuclei become more and more neutron-rich as you descend. At the surface, you have iron with 26 protons and around 30 neutrons, the kind of nucleus you find in any iron atom on Earth. A few hundred meters below the surface, you have nuclei with the same 26 protons, but 40 or 50 neutrons isotopes that on Earth would be radioactive and rapidly decay, but in the dense neutron star crust are stable because the surrounding conditions energetically favor them. Deeper still, you have nuclei with 50 protons and 120 neutrons. Deeper still, nuclei with 100 protons and several hundred neutrons. The chemistry of the crust shifts continuously layer by layer toward more and more neutron-heavy compositions. There is a depth somewhere around half a kilometer below the surface where this trend hits a physical limit. The nuclei have absorbed as many neutrons as they possibly can, and any additional pressure pushes some of those neutrons out of the nuclei and into the spaces between them. Free neutrons begin to leak out and form a fluid that flows through the crystalline lattice of the remaining nuclei. This depth is called the neutron drip line, and below it the structure of the crust is no longer a simple ionic lattice. It is a complex two-component system with neutron-rich nuclei still arranged in a lattice and a sea of free neutrons flowing through the gaps between them. The matter below the drip line is partially solid, partially fluid, and behaves in ways that have no everyday analog. Even more strangely, in the deepest part of the inner crust, just before you reach the boundary with the outer core, the nuclei do something that physicists have given a deeply unscientific set of names. They deform. The pressure from the surrounding fluid of free neutrons becomes so intense, and the energetic balance between the nuclear surface and the surrounding medium becomes so finely tuned that the nuclei start to merge with each other in elongated and sheet-like and tube-like configurations. Computer simulations show the nuclei distorting into shapes that look in cross-section like various pasta shapes. There are layers of gnocchi, roughly spherical nuclei sitting in regular arrangements. There are layers of spaghetti where the nuclei have stretched into long tubes. There are layers of lasagna where the nuclei have flattened into parallel sheets, separated by sheets of fluid neutrons. There are even more exotic shapes that physicists call anti-spaghetti and Swiss cheese, where the structure inverts and the fluid neutrons form tubes inside a continuous nuclear medium. The names sound like a joke, but they are the actual technical terminology used in the published literature. Physicists writing papers on the inner crust of neutron stars use phrases like the lasagna phase and the gnocchi phase without any irony. The reason the name stuck is that the simulations really do show shapes that look exactly like those pasta types in cross-section, and once you have seen the simulation output, no other naming system feels appropriate. The shapes themselves are a consequence of the energetic competition between the nuclear surface tension, which wants to keep the nuclei spherical, and the strong attraction between protons and the surrounding electron sea, which wants to spread the nuclear material out as widely as possible. At the bottom of the inner crust, that competition produces these strange, elongated and flattened structures, and the nuclear pasta layer occupies maybe a few hundred meters of depth before giving way to a fully fluid outer core where no discrete nuclei exist at all. The crust, all of it, from the iron lattice at the surface down to the pasta layer at the inner crust boundary, is the part of the neutron star where some of the most observable phenomena occur. Because the crust is rigid and brittle, it can crack. It does crack, in fact, regularly, as the gravitational and magnetic stresses on the star evolve over time. When the crust cracks, the energy released travels through the star in the form of seismic waves and radiates outward as bursts of X-rays and gamma rays. The events are called starquakes, and they are observable from Earth. Starquakes from regular pulsars are usually small, producing small glitches in the otherwise extremely regular timing of the radio pulses. The glitches reveal that something abrupt has happened to the rotation of the star, usually because a portion of the crust has cracked and the moment of inertia has shifted slightly. Pulsar timing is precise enough that these glitches can be measured to fractions of a microsecond, and decades of pulsar timing data have produced a rich record of starquake events across hundreds of neutron stars. Starquakes from magnetars are much more dramatic. The magnetic field of a magnetar 1,000 trillion times stronger than Earth's exerts enormous stresses on the crust. When the field configuration shifts, or when a section of the crust gives way under the magnetic pressure, the resulting starquake can release more energy in a fraction of a second than the Sun puts out in 100,000 years. The 2004 SGR 1806-20 event we mentioned earlier was the most extreme magnetar flare ever observed. The flare delivered enough soft gamma rays to ionize a significant portion of the upper Earth atmosphere, even though the magnetar was 50,000 light-years away. Had it been within a few light-years of us, the consequences for life on Earth would have been considerably worse than ionizing the upper atmosphere. We are extremely fortunate that none of the known magnetars sit anywhere close to us. The magnetic field itself sitting in and around the crust is one of the more interesting features of any neutron star. Where does that field come from? The original star before its supernova had a relatively modest magnetic field comparable to the field of an ordinary main sequence star. When the core collapsed during the supernova, the field lines that had been spread out over a stellar-sized volume got compressed along with the matter. A field that originally threaded through a region of space tens of millions of miles across got squeezed into a region only 12 miles across. The field strength scales inversely with the area through which it passes, so the compression amplifies the field by an enormous factor. The resulting neutron star magnetic field is roughly 1 trillion times stronger than Earth's for an ordinary pulsar, and 1,000 times stronger still for a magnetar. The field is anchored in the crust, frozen into the iron lattice, and the underlying superconducting protons and its slow decay over millions of years drives much of the long-term evolution of the star. For an observer on Earth, looking at a neutron star with the right instruments, the crust is the only part of the star you can really study directly. The thermal emission from the surface depends on what the crust is made of and how heat is conducted through it. The pulsations from a rotating pulsar depend on the geometry of the magnetic field above the crust. The starquake glitches and the magnetar flares depend on how the crust cracks and rearranges itself. Even gravitational waves from neutron star mergers carry information about the crust, because the elastic response of the crust influences how the two stars deform and ultimately tear each other apart in the final moments before merger. Almost everything we measure about a neutron star, with the partial exception of the gravitational mass and the radius, is filtered through the behavior of the outer few kilometers of material. The deeper interior is hidden from direct view, accessible only through theoretical inference combined with whatever surface signatures it manages to imprint on the crust above it. This filtering effect is one of the reasons the deep interior is so difficult to study. Astronomers measure what they can see. What they can see is, for the most part, the light coming off the crust. To draw conclusions about the matter inside the core, they have to combine those surface measurements with theoretical models of how the matter inside should behave, and check whether the models predict surface behaviors consistent with the observations. It is a kind of indirect physics, where you reason about an inaccessible interior by checking the consistency of theoretical predictions against accessible exterior data. We will see this kind of reasoning in much more detail when we get to the Helsinki paper, which is essentially a sophisticated version of exactly this approach. Below the inner crust, with its pasta and its dripping neutrons and its sheets of nuclear lasagna, you reach the boundary of the outer core. This is the layer where the nuclei finally dissolve completely. There are no more discrete protons and neutrons bundled into nuclei. There is just a continuous fluid, mostly neutrons, with about 10, 10% protons and an equal number of electrons flowing as a quantum medium under the pressure of everything above it. The behavior of that fluid and the strange superfluid and superconducting properties it exhibits is where we go next. The descent continues. We are still kilometers above the very deepest part of the star, where matter does the thing this script is really about. But each step inward takes us further from any familiar physical state and closer to the matter that almost certainly does not exist anywhere else in the universe. Below the inner crust, the structure of matter changes again, and this time the change is more complete than anything that came before. The discrete nuclei that had been the basic units of the crust are gone. The pasta phases that had marked the deepest layer of the crust have given way to a continuous medium. There is no more lattice. There is no more atomic structure in the everyday sense. What you have descending through the outer core of a neutron star is a fluid of neutrons with about 10% protons and an equal number of electrons mixed in, flowing in a way that is unlike any fluid you have encountered in your daily life. The matter is held together by gravity from above and by quantum mechanical pressure from within. The pressure is the key, and it is worth understanding properly because it is the same pressure that holds up white dwarf stars and neutron stars, and that ultimately fails inside black holes. The pressure is called degeneracy pressure, and it is a consequence of one of the most surprising rules in quantum mechanics, the Pauli exclusion principle. The principle, articulated by the Austrian physicist Wolfgang Pauli in 1925, states that no two identical fermions can occupy the same quantum state at the same time. Neutrons are fermions, so are electrons and protons. Every fermion in any system has to sit in its own unique combination of position, momentum, and spin. There is no doubling up. Two electrons cannot share a quantum state. Two neutrons cannot share a quantum state. Each one needs a slightly different set of quantum numbers from every other one in the same physical region. In ordinary matter, at ordinary temperatures, this rule has subtle consequences, but does not dominate the physics. The available quantum states are mostly empty with thermal motion, spreading the particles across many possible states, and there is always plenty of room for any given particle to find a state that no other particle is occupying. The gas in your room, for example, has so many available states for each molecule that the exclusion principle barely matters in everyday calculations. In a white dwarf or a neutron star, the situation is different. The matter has been compressed so much that the quantum states have been packed full from the lowest energies up to some maximum energy called the Fermi energy. Every state below the Fermi energy is occupied. Every state above is empty. The fermions cannot pile into lower energy states because those are full. They cannot rest because resting would mean being at zero momentum, and zero momentum states are full. They are forced to occupy higher and higher energy states, and that means they are forced to be in motion, even though the temperature might not justify the motion in any thermodynamic sense. This is the source of degeneracy pressure. The fermions blocked from sharing low energy states by the exclusion principle push against each other with a quantum mechanical force that has nothing to do with thermal energy. The pressure rises with density. The denser the matter, the higher the maximum occupied energy state, the faster the fermions have to be moving, and the higher the outward pressure they exert on whatever is trying to compress them. In a white dwarf, this pressure is provided primarily by the electrons, and it is enough to balance the gravitational compression of an object up to about 1 4/10 solar masses. Above that mass, called the Chandrasekhar limit, and worked out by the young Indian astrophysicist Subrahmanyan Chandrasekhar in 1930, while travelling by ship from India to Cambridge Electronics degeneracy pressure can no longer hold up the matter. The white dwarf collapses, the electrons get squeezed onto the protons, and you end up with a body composed primarily of neutrons. In a neutron star, the degeneracy pressure is provided by the neutrons themselves, which are roughly 2,000 times more massive than electrons. The pressure they can produce at any given density is correspondingly higher than what electrons alone could manage. That is why neutron stars are stable at densities far higher than any white dwarf. The exclusion principle still applies, but now it is the neutrons that are forced to occupy higher and higher energy states as the matter is compressed, and the resulting pressure is what holds the star up against its own gravity. Now here is where the strangeness of the outer core gets interesting. The neutrons in the outer core, despite being at temperatures of millions of degrees, are in a quantum state that is by certain physical measures colder than anything you can produce in a laboratory on Earth. Temperature, in the relevant sense, has to do with how much the particles are moving relative to the energy associated with their quantum states. If a fermion has a Fermi energy corresponding to billions of degrees, but the actual thermal motion only corresponds to millions of degrees, then in the relevant comparison, the matter is cold. Its thermal motion is a small perturbation on top of the dominant degeneracy energy. By that measure, the neutrons in the outer core of a neutron star are sitting in a quantum degenerate fluid in a regime more similar to the liquid helium in a low-temperature physics laboratory than to anything we usually call hot. This matters because at sufficiently low effective temperatures, the neutron fluid undergoes a phase transition into a superfluid state. A superfluid is a fluid that has zero viscosity, meaning it flows without any internal friction. Once you set part of a superfluid in motion, that motion persists indefinitely because there is no friction to dissipate it. Superfluids on Earth made of liquid helium-3 or liquid helium-4, cooled to fractions of a degree above absolute zero, exhibit weird behaviors. They can flow up the sides of the containers and out the top against gravity. They can leak through pores too small for an ordinary fluid to pass. They support quantized vortex lines, swirls of fluid motion that come in discrete units rather than continuous gradations. The neutrons in the outer core of a neutron star do all of these things scaled up to the dimensions of a small city. The neutron fluid is a superfluid. It flows through the matter without friction. It supports vortex lines threading the interior of the star. The vortex lines are pinned to defects in the surrounding crust, and as the star slows down over time, due to magnetic braking, the vortex lines occasionally unpin and rearrange themselves, transferring rotational energy from the superfluid interior to the rigid crust. This is one of the leading models for what causes pulsar glitches, the small but observable speed-ups in pulsar rotation rates that have been recorded for decades. The vortex unpinning model connects the otherwise mysterious surface phenomenon to the deep quantum behavior of the neutron fluid below. The protons in the outer core do something equally strange. They are too few in number to dominate the pressure, but they are still present about 10% of the matter by particle count. At the temperatures and densities involved, those protons form a different kind of quantum mechanical state called a superconductor. A superconductor, like a superfluid, is a low-temperature quantum state, but instead of supporting frictionless flow of a neutral fluid, it supports frictionless flow of an electric current. The proton superconductor in the outer core of a neutron star carries the magnetic field of the star without resistance, channeling the field lines into discrete tubes called fluxoids. The configuration of those fluxoids threading through the proton superconductor partly determines the long-term evolution of the magnetic field as the star ages. We have very good reason to believe this is happening, but the details are still being worked out by theorists, and direct observational confirmation is very hard. The electrons, the third component of the outer core, do not form anything as exotic as a superfluid or a superconductor. They are simply a degenerate Fermi gas free to flow through the lattice of vortex lines and fluxoids set up by the neutrons and protons, providing their own contribution to the local pressure and to the overall electrical neutrality of the matter. Electrons are nearly 2,000 times less massive than nucleons, so their degeneracy contribution to the pressure is small in absolute terms, but they have to be there to balance the positive charge of the protons. Without them, the matter would not be electrically neutral, and the resulting electric fields would be enormous. So the picture of the outer core taken as a whole is this: a continuous fluid, mostly neutrons. The neutrons in a superfluid state flowing without friction, supporting quantized vortex lines that thread the interior of the star. About 10% of the matter as protons in a superconducting state, channeling the magnetic field into discrete fluxoids. About 10% of the matter as electrons in a degenerate Fermi gas flowing freely through the medium. All of it in equilibrium under the gravitational pressure of the matter above and the degeneracy pressure of the components themselves. None of it resembling even approximately any state of matter you have encountered in your everyday life. The thickness of the outer core is several kilometers. As you descend through it, the density rises continuously from a few times the density of an atomic nucleus at the top to perhaps 10 or 20 times nuclear density at the bottom. The matter is the same composition throughout, mostly neutrons with smaller fractions of protons and electrons, but the pressure and the speed of sound and the various thermodynamic properties shift smoothly with depth. There is no sharp boundary inside the outer core. There is just a continuous quantum fluid getting denser as you go deeper. There is a way to summarize this kind of behavior mathematically that physicists call the equation of state. The equation of state of a substance is simply the relationship between its pressure and its density at any given temperature. For an ordinary gas at room temperature, the equation of state is the familiar ideal gas law, which says that pressure rises linearly with density and with temperature. For more complicated substances, the relationship is more complicated. For neutron-star matter, the equation of state is one of the great open theoretical questions of nuclear physics. It depends on what the matter is made of, how the various components interact with each other, what kinds of quantum mechanical effects dominate at different densities, and whether any phase transitions occur as the density rises. Different theoretical assumptions produce different equations of state, and different equations of state predict different observable properties for real neutron stars. Different maximum masses, different radii at any given mass, different gravitational wave signatures during mergers. A great deal of contemporary neutron star research is essentially a contest between different proposed equations of state, with new observations gradually narrowing down which ones are still viable. The 2017 GDUM70817 merger we mentioned earlier was a landmark in this contest because the gravitational wave signal of the inspiral phase carries direct information about how each star deformed under the tidal pull of its partner, and the EAT deformation depends sensitively on the equation of state. A stiffer equation of state where matter resists compression strongly produces less tidal deformation and a more compact gravitational wave signature. A softer equation of state where matter is more compressible produces more tidal deformation. The GW17-817 signal favored equations of state that are not too soft, ruling out a substantial portion of the previously proposed models. subsequent events have continued to refine the picture. The eventual goal is a complete observationally confirmed equation of state for neutron-star matter at all the relevant densities from the surface to the deep core. Then, somewhere near the bottom of the outer core, the picture starts to change. The pressures involved approach values where the neutrons themselves begin to lose their identity. The strong force that normally holds the three quarks inside each neutron into a confined bound state begins to lose its grip. The matter is approaching a phase transition in some ways analogous to the transition from solid to liquid, or from liquid to gas, but in a regime that physics has never tested directly in the laboratory. What lies on the other side of that transition is the inner core. And what the inner core is made of is the question that the entire scientific story of this drift has been building toward. Whether the inner core is still made of neutrons just at higher density, or whether it has crossed the boundary into a regime of free quarks and undergone the deconfinement transition, has been one of the great open questions of dense matter physics for 40 years. The Helsinki team's 2023 result, which we will get to shortly, says that the deconfinement transition probably has occurred with somewhere between an 80 and 90% likelihood. But to understand what that result means and why it is so significant, we have to spend some time first with the question itself. We have to understand what the alternatives are and why the answer has been so hard to settle, and what changed in the last few years to allow the Helsinki group to assign a probability at all. That is the next piece of the descent, not a deeper layer in the literal sense, a deeper question suspended over the matter at the bottom of the star. We will get to the layer itself soon enough. But first the puzzle. First the long-standing problem of what the deepest matter is doing and why it has resisted being pinned down for so long. We have been descending through layers we understand fairly well. The atmosphere we understand. The crust we understand with some open questions about the nuclear pasta, but a generally clear theoretical picture. The outer core with its superfluid neutrons and superconducting protons we understand reasonably well, even if some details about exactly how the superfluid couples to the rest of the star remain active research topics. By the time you get to the bottom of the outer core, somewhere around 8 or 9 kilometers below the surface, you are still on relatively firm theoretical ground. Nuclear physics, condensed matter physics, and quantum statistical mechanics together can describe what is going on with reasonable confidence. But then you reach a depth where the firm ground gives way. The matter in the inner core, the deepest portion of a massive neutron star, sits at densities and pressures that no laboratory on Earth has ever produced, and that no laboratory on Earth seems likely to produce in the foreseeable future. Theoretical physics can still apply its general principles to this regime, but the principles do not give a unique answer. Different sets of reasonable assumptions produce different predictions for what the matter is doing, and the predictions differ in physically substantial ways. Until very recently, there was no rigorous method for choosing between them. The inner core was a black box surrounded by a halo of theoretical possibilities, with no way to weigh which possibility was most likely to be correct. The basic question is this: as you compress matter beyond a few times nuclear density, what happens to the neutrons? Do they remain as discrete neutrons, just packed tighter than they would normally be, exerting their degeneracy pressure as before, but with the addition of stronger repulsive nuclear interactions at short range? Do they transform into other kinds of baryons, like the hyperons we mentioned earlier, which contain strange quarks, alongside the up and down quarks of an ordinary neutron? Do they retain their individual identities at all? Or do they undergo a phase transition similar to the way ice transitions to water and water transitions to steam into a fundamentally different state, where the quarks inside each neutron break free of their host particle and roam through the medium as a continuous quark fluid. Each of these possibilities in the literature has its serious defenders. Each has been worked out theoretically. Each predicts slightly different observable properties for the resulting neutron stars, and each has its own characteristic signature in the various ways we have of testing the equation of state. Let me walk through them because the alternatives matter for understanding why the Helsinki result is significant. The most conservative possibility is that the inner core is just neutrons all the way down. Even at extreme densities, the protons and neutrons retain their identities, and the equation of state is determined by ordinary nuclear physics extrapolated from the densities we can study in nuclei here on Earth, out to the densities present in the deepest stellar interiors. Many calculations have been done in this regime using various approximations and models. They tend to predict equations of state on the stiffer end of the spectrum, with relatively rapid increases in pressure as the density rises. Stiff equations of state allow neutron stars to support relatively high masses and to have relatively large radii. The known existence of two solar mass neutron stars, like the pulsar known as PSR J0740+6620, measured by NICER and by radio timing campaigns, places strong constraints on how soft the equation of state can be. Pure neutron matter with the right interaction models can produce the observed maximum masses, but only if the matter remains relatively stiff at high densities. The second possibility is that hyperons appear. Hyperons are particles that contain at least one strange quark in addition to the up and down quarks of ordinary baryons. The most relevant hyperons for neutron star physics are particles called the lambda and the sigma, which are the lightest hyperons and the most likely to appear at high densities. The basic logic is energetic. As the density rises, the neutrons are forced into higher and higher quantum states, requiring more and more energy. At some point, it becomes energetically favorable to convert some of those high-energy neutrons into hyperons, which are themselves slightly heavier than neutrons, but provide additional quantum states to occupy. Once hyperons appear, the equation of state softens because the system has new low-energy states to fill, instead of being forced to keep adding higher and higher energy neutrons. A softer equation of state means the matter is more compressible, and that limits the maximum mass a neutron star can support. This is the so-called hyperon puzzle. Most realistic calculations of hyperon-rich matter predict softer equations of state than would be needed to support two solar mass neutron stars. But two solar mass neutron stars exist. So either the hyperon calculations are missing some important physics that keeps the equation of state stiffer than naive predictions suggest, or hyperons do not appear in significant quantities at neutron star densities, or some other mechanism prevents the predicted softening. The hyperon puzzle has been debated in the literature for decades. There is no clean resolution. Various theoretical fixes have been proposed, but none have achieved consensus. It is worth pausing on the hyperon puzzle for a moment, because it illustrates how subtle the inner core problem really is. The basic concern is that we have one observation, the existence of pulsars heavier than two solar masses, that places a hard constraint on the equation of state. Whatever the matter is doing inside, it has to be stiff enough to hold up that much mass against gravity. And we have a theoretical argument based on the standard energetic logic of nuclear physics that says hyperons should appear at high densities and should soften the equation of state. The two ideas taken at face value conflict. Either the observations are wrong, which seems unlikely given how many independent groups have measured the high mass pulsars, or the simple energetic argument for hyperons is incomplete in some way that has not yet been fully understood. The puzzle has driven a substantial industry of theoretical work, with various physicists proposing modifications to the hyperon-nucleon interactions, additional repulsive forces at short distances, or alternative phase transitions that prevent the hyperon population from growing as predicted. Each proposal explains the puzzle in a way that requires its own set of assumptions. None has emerged as the clear winner. My chair. The third possibility, the one this whole script has been building toward, is the deconfinement transition. At sufficiently high densities, the strong force between quarks weakens enough that the boundaries between individual hadrons effectively dissolve. The quarks become free to roam through the medium as a continuous fluid. This is the so-called deconfined quark-matter phase, also sometimes called color-flavor-locked matter, or strange quark matter, depending on the specific composition assumed. The basic prediction comes from quantum chromodynamics, the theory that governs the strong nuclear force. At high densities, the QCD coupling constant decreases in a phenomenon called asymptotic freedom, which was first worked out theoretically in the early 1970s by David Gross, Frank Wilczek, and David Politzer, who later shared a Nobel Prize for the work. Asymptotic freedom means that at sufficiently small distances, or equivalently sufficiently high densities, the strong force between quarks becomes weak, and quarks behave more like free particles than confined ones. Asymptotic freedom is a strange property the more you think about it. Most forces in nature get weaker as the things they act on get farther apart. Gravity, electromagnetism, and the weak force all decrease in strength with distance. The strong force between quarks does the opposite. At short distances, the strong force is weak. At longer distances, the strong force gets stronger, eventually rising so much that it becomes physically impossible to separate two quarks. The energy required to pull them apart becomes so high that before you can succeed, the energy itself converts into new matter, producing additional quark-antiquark pairs, and the result is that you can never isolate a single quark in ordinary conditions. This is called confinement, and it is why we never see free quarks in everyday matter. Quarks only exist inside hadrons locked together by the strong force in groups of 2 or 3. The flip side of confinement is asymptotic freedom. At very short distances, much smaller than the size of an ordinary hadron, the strong force is weak. Push the quarks close enough together, and they start behaving like free particles. The question for neutron-star physics is whether the densities present inside the inner core push the quarks close enough together for asymptotic freedom to take over. If yes, then the matter at the bottom of the most massive neutron stars is in a deconfined state with quarks flowing freely through the medium. If no, then the matter is still in its confined phase with quarks locked inside their host hadrons, even at extreme densities. The question is whether the densities present inside neutron stars are high enough for asymptotic freedom to take over. The answer, calculated from the QCD equations directly, is uncertain. Perturbation theory, the most widely used general technique for QCD calculations, works well at very high densities, far above what is reached even in the cores of neutron stars. It works less well at the moderate densities of nuclear matter. Neutron star cores sit awkwardly in between these two regimes, where neither limiting approximation applies cleanly. Calculations have to extrapolate from one regime to the other, and different extrapolation methods give different answers about exactly when the deconfinement transition would occur. What is generally agreed is this: if neutron stars are massive enough, and if the densities at their cores rise high enough, then deconfinement should occur. Below some threshold density, the matter is confined with quarks locked inside discrete hadrons. Above the threshold, the matter is deconfined with quarks free to flow through the medium. The transition might be sharp like the boiling of water at a fixed temperature, or it might be gradual, like the gradual loss of magnetic ordering as a metal warms up through its Curie temperature. The details depend on aspects of the QCD calculations that are themselves still being refined. But the existence of the transition in some form is essentially guaranteed by the underlying physics. The question is only at what density it occurs, and whether the cores of real neutron stars actually reach that density. For decades, the answer to that question was simply unknown. Different theoretical groups produced different predictions. Some predicted that the transition occurs at densities just barely above what is reached in the cores of two solar mass neutron stars, which would mean that some of the most massive observed neutron stars contain quark-matter cores. Others predicted that the transition occurs at higher densities requiring star masses or core densities that exceed what is observed. Still others predicted intermediate cases where some but not all observed neutron stars contain quark matter. There was no consensus. The reason it has been so hard to settle is that the observational tests are all indirect. We do not see the inner core. We see at most the surface and the gross properties of the star, its mass, its radius, its rotation rate, its tidal response during mergers. From those properties, we have to infer what is going on inside. The inference is sensitive to assumptions about the entire equation of state from the surface to the core, and small changes in those assumptions can shift the inferred core composition substantially. Combined with the theoretical uncertainty about the transition density itself, the result has been a research field that has been unable to converge for 40 years. What changed in the last few years is the combination of better observational constraints and a more rigorous statistical methodology for combining them. The observational side has produced in the 2010s and 2020s much better measurements of neutron star masses and radii than were available previously. The PSR J0740+6620 measurements from NICER, the GW170817 tidal deformability constraints from LIGO and Virgo, and various radio timing campaigns of binary pulsars have together pinned down the mass-radius relation for neutron stars with the tightest precision astronomers have ever achieved. The theoretical side has refined the QCD calculations at both low and high densities, narrowing the range of possible equations of state. And the statistical methodology has caught up to the data with Bayesian inference techniques that take all of these constraints together and ask, in a quantitative way, what is the probability that any given equation of state is correct, given all the available evidence. This is the methodology that the Helsinki group used in their 2023 paper, and it is what allowed them for the first time to assign a probability to the question of whether massive neutron stars contain quark matter cores. They did not prove that the cores contain quark matter. They calculated, given everything we know, how likely it is. The answer, as we mentioned at the beginning, came in at between 80 and 90%. That is the result we are going to walk through carefully in the next section. How they did it, what their methodology actually involved, why the answer is what it is and what it means for our understanding of dense matter. The puzzle, in other words, may finally be moving toward a resolution. Not through a single dramatic discovery, but through the slow accumulation of better observations, better theory, and better statistical tools, all combining to push the field toward a consensus that has eluded it for decades. The Helsinki paper is the clearest expression of that progress to date. It is what we are going to spend the next stretch of this drift with. The paper appeared in Nature Communications in December of 2023. Its lead authors were Jonas Hirvonen, a doctoral student at the University of Helsinki, and Jonas Nattila, a researcher with appointments at Helsinki and at Columbia University, working with Vuorinen, the senior physicist at Helsinki, who leads the broader research group on quark-matter and high-density QCD. The paper was the culmination of several years of work by the same team, building on an earlier 2020 paper that had appeared in Nature Physics. The 2020 paper had presented the first systematic argument that massive neutron stars probably contain quark-matter cores. The 2023 paper sharpened that argument substantially, used a more rigorous statistical methodology, and produced the headline number we have been circling around for this entire drift, between 80 and 90%. The probability, given everything we currently know, that the cores of two solar mass neutron stars contain deconfined quark matter. Let me walk through what the team actually did, because the methodology matters. It is not enough to say they did a Bayesian analysis. The interesting question is what they fed into the analysis, what assumptions they made, and how they translated those assumptions into a probability statement. The first ingredient was a comprehensive set of observational constraints on neutron star properties. The team gathered the published mass and radius measurements for the heaviest known pulsars, including the X-ray timing measurements from NICER for stars like PSR J0740+6620, the gravitational wave constraints from the GW170817 merger, and various radio timing measurements of pulsars in binary systems. They organize these constraints into a coherent likelihood function, which is the mathematical object that tells you for any candidate equation of state how likely it is that you would have observed the data that has actually been observed. The second ingredient was a set of theoretical anchor points derived from first principles calculations of QCD. At low densities near the density of an ordinary atomic nucleus, nuclear physics calculations using methods called chiral, effective field theory, provide reliable predictions for the behavior of matter. At very high densities far above what is reached, even in the cores of neutron stars, perturbative QCD calculations provide reliable predictions. The team used both of these theoretical regimes as boundary conditions. Whatever the equation of state was doing in the intermediate regime, where neutron stars actually live, it had to match these well-understood limits at the low and high ends. The third ingredient was a parameterization of the equation of state itself. The team did not assume any specific theoretical model. Instead, they parameterized the equation of state with a set of flexible mathematical functions that could, in principle, accommodate any plausible behavior between the low density and high density anchors. This is the key methodological move, and it is what distinguishes a Bayesian analysis from a more conventional model comparison approach. Rather than testing a small number of specific models against the data, the team allowed the equation of state to vary continuously across the entire space of possibilities, and they let the data and the theoretical anchors decide which regions of that space were favored. The fourth ingredient was the computer time to actually carry out the calculation. The phase space of possible equations of state is enormous, and the calculation required millions of CPU hours of supercomputer runs to sample it adequately. Hirvonen, in his published comments on the paper, emphasized this aspect. The team used the resources of the Finnish supercomputer center called CSC, located in Espoo near Helsinki. CSC operates several large high-performance computing facilities, and the Helsinki group used them to run their Bayesian sampling code, generating millions of candidate equations of state and weighting each one by how well it matched the observational and theoretical constraints. The output of all this work was a probability distribution over the entire space of possible equations of state given everything we currently know. From that distribution, the team could ask very specific questions. What is the probability that the matter at any given density is in a deconfined state? What is the probability that the cores of two solar mass neutron stars contain quark matter? What is the probability that the deconfinement transition has occurred at a specific density? The headline answer was the one we have been talking about. For neutron stars near two solar masses, which is the highest mass at which neutron stars are commonly observed, the probability that the matter at the very center is in a deconfined quark matter phase comes out at between 80 and 90%, depending on which precise version of the analysis is used. Some related write-ups, particularly the press release from the University of Stavanger, where one of the collaborators was based, give the range as 75 to 90%. The exact range depends on small variations in how the analysis is set up, but the broad picture is robust. Most of the probability is concentrated in scenarios where massive neutron stars do contain quark matter. There are a few specific aspects of the result worth highlighting. First, the result is mass dependent. For lower mass neutron stars around 1 4/10 solar masses, the probability of a quark matter core is much lower. The matter in those stars is with high probability still in a confined state. This makes sense physically. Lower mass neutron stars have lower central densities because their gravity is not as strong as in heavier stars, and the deconfinement transition simply does not occur at the densities they reach. The transition is something that happens only as you go to the higher masses where the central pressures are forced to be higher to support the additional weight. Second, the result implies a specific relationship between the equation of state and the maximum mass that neutron stars can support. The deconfinement transition in most of the favored equations of state produces a softening of the matter at the relevant densities, which limits how heavy a neutron star can be before collapsing into a black hole. The Helsinki analysis, combined with the observed maximum masses, points toward a maximum stable neutron star mass of somewhere between 2 and 2 1/4 solar masses. Above that, the matter cannot support itself, and you get a black hole instead. Third, the result has implications for what neutron star mergers should look like. The 2024 follow-up paper from the same Helsinki group, published as a series of more technical analyses through that year, looked at how quark matter would behave during the violent dynamics of a binary neutron star merger. They used two independent theoretical methods. One was a holographic approach, drawing on connections between QCD and certain gravity calculations in higher dimensional spaces. The other was perturbation theory in QCD, suitable for the high-density limit. To the team's satisfaction, the two methods gave matching results for the bulk viscosity of quark matter at the relevant densities and temperatures. The agreement was a meaningful piece of theoretical confirmation. Two very different ways of approaching the same question converged on the same answer. The bulk viscosity result matters for a specific reason. When two neutron stars merge, the resulting object oscillates violently for a few milliseconds before either settling into a heavier neutron star or collapsing into a black hole. During those oscillations, the matter inside the merger remnant is being squeezed and stretched, with different regions experiencing rapid changes in density and temperature. How the matter responds to those changes, particularly how much energy gets dissipated as the matter is being driven out of equilibrium, is determined by its bulk viscosity. If the matter is in a deconfined quark matter phase, the bulk viscosity has a different temperature and density dependence, than if the matter is in a confined hadronic phase. The two phases respond to merger oscillations differently. The differences should in principle be detectable in the post-merger gravitational wave signal, although current detectors are not quite sensitive enough to make the discrimination cleanly. Future detectors, including the planned Cosmic Explorer in the United States and the Einstein telescope in Europe, will be sensitive enough to test the prediction directly. The Helsinki group's bulk viscosity calculation, by establishing what the prediction actually is for quark matter, has provided a target for future observations to aim at. This is how scientific knowledge tends to consolidate in real time. A new theoretical result like the 2023 paper opens up a clearer picture of what the matter inside neutron stars is probably doing. A follow-up calculation like the 2024 bulk viscosity work refines the picture and provides predictions for future observations. New detectors in turn get built with those predictions in mind. The whole process iterates over years and decades, with each new piece of information narrowing the space of possibilities and tightening the constraints on what the matter actually is. Vuorinen, in interviews about the work, has emphasized what the result means scientifically. For decades, the existence of quark matter inside neutron stars was a theoretical possibility, defended by some theorists, dismissed by others, untested by any direct experiment. With the 2023 paper, the picture shifted. The existence of quark matter cores became for the first time the most likely explanation for the observed neutron star data, with a quantitatively assigned probability. Not a proof, not a certainty, but a quantitative best estimate calculated from the actual observations using the actual underlying physics, with the actual uncertainties propagated correctly. It is worth noting that the Helsinki team is not the only group working on this question. Several other research collaborations around the world are pursuing related approaches. Groups in Germany and Japan, in the United States, in Italy and elsewhere have published their own statistical analyses of dense matter equations of state, sometimes using different parameterizations, sometimes incorporating different sets of observational data, sometimes weighting the theoretical anchors differently. The results from these different groups are not always identical, but they are broadly consistent. Most current analyses point in the same general direction the Helsinki group has pointed. Massive neutron stars probably contain something other than ordinary nuclear matter at their cores, and quark matter is the leading candidate for what that something is. The convergence across multiple independent groups is in itself evidence that the picture is on the right track. Different teams using different methods would not all converge on the same probability range if the underlying physics were unstable to small changes in assumptions. Some of the difference between groups comes down to how the boundary regions are handled. The lowest density regime near nuclear density can be handled with chiral, effective field theory, but different teams use different orders of the perturbation series and different choices of low energy constants. The highest density regime, well above neutron star core densities, can be handled with perturbative QCD, but again, different teams use different orders of the calculation. The intermediate regime, where the neutron star matter actually sits, is where most of the methodological choices matter, and different teams parameterize the equation of state differently. Despite these differences, the trend is consistent. The era of unreserved disagreement about the inner core is ending. The era of quantitatively constrained probabilities is beginning. It is worth being clear about what the result is and is not. It is not a discovery in the strict experimental sense. Nobody has ever isolated a sample of quark matter from inside a neutron star. Nobody has produced a smoking gun signature like a sharp transition in some observable, that uniquely indicates quark-matter cores. What the result is the most rigorous statistical statement that can currently be made about the question given the available data and the available theoretical tools. Future observations, particularly more gravitational wave detections of neutron-star mergers and more X-ray timing measurements from NICER and its successors, will refine the result. The probability might rise or it might fall depending on what the new data shows. But the methodology now exists for combining all available information into a single quantitative answer, and the current best answer is between 80 and 90%. I want to spend a moment on what this means at a level that is more philosophical than technical, because I think it is one of the more interesting things to sit with. Quark matter, if it exists in the cores of massive neutron stars, is matter that we can never directly access. We cannot bring it to a laboratory. We cannot recreate it on Earth in any stable form. The closest we have come is the quark-gluon plasma, produced in heavy ion collisions at the Large Hadron Collider and at the Relativistic Heavy Ion Collider on Long Island. But those samples are extremely hot, and they exist for less than a fraction of a billionth of a second before the colliding nuclei separate and the plasma cools down. Cold, stable, gravitationally confined quark matter, the kind that may exist inside neutron stars, has never been produced in any laboratory. What the Helsinki analysis tells us is that this matter exists anyway, out there in the cores of dead stars in numbers that probably reach into the hundreds of millions across the galaxy. We will probably never see it directly. We will probably never bring a sample home. But we now have very good reason to believe it is there doing whatever cold, dense quark matter does, sitting in the dark beneath kilometers of crust and outer core in the inner cores of every massive enough neutron star. This is the result that the entire script has been moving toward. We have descended through every layer of the star, from the atmosphere through the crust and the pasta phases through the outer core, with its superfluid neutrons and superconducting protons, and on into the inner core with its long-standing puzzle. And now, with the Helsinki paper, the puzzle has shifted. The most likely answer to what is the matter doing at the very center of a massive neutron star is at last on the table with a quantitative probability attached. What that answer means for the larger picture of what these objects are and what they connect to in the rest of the universe is what we turn to next. Let us take a step back away from the technical details of the Helsinki paper and sit with what its result actually says about the universe we live in. Because the science, when you let it settle, has a quiet strangeness to it that is worth letting yourself feel. There is matter in the cores of massive neutron stars that is not made of the same stuff that anything else in the visible universe is made of. The atoms in your body, the molecules in the air you breathe, the rocks under your feet, the gas inside ordinary stars, the dust in interstellar space, every form of matter you can name, and most that you cannot, are all built out of a few common ingredients. Hydrogen and helium dominate by particle count. Heavier elements appear in smaller proportions, but they are all made the same way, with protons and neutrons bound into nuclei with electrons orbiting in their various quantum shells. The chemistry varies, but the underlying ingredients do not. From the surface of a star to the surface of a planet, to the inside of a living cell, you are dealing with the same particles arranged in different ways. The matter inside the inner core of a massive neutron star is, with the high probability the Helsinki team calculated, not made of those particles. It is not made of atoms. It is not made of nuclei. It is not made of discrete protons or neutrons. It is made of quarks freed from their host particles by the pressure of an entire collapsed star pressing down on them, flowing as a continuous medium that has no analogue in any other state of matter we have ever encountered. The matter is in the most literal physical sense doing something different from what every other piece of visible matter in the universe does. This is genuinely unusual. Most of the time when we discover a new exotic state of matter, it turns out to be a variant of something more familiar. Plasma is just gas with the electrons stripped off. Bose-Einstein condensates are just very cold quantum systems behaving in an unusual but understandable way. Even the quark-gluon plasma produced at heavy ion colliders is just a hot version of confined nuclear matter where the boundaries between particles have momentarily dissolved. But cold, stable, gravitationally confined quark, matter the kind that probably sits in neutron-star inner cores, is something genuinely different. It is matter at densities and pressures that no other process in the universe produces stably. It exists only because gravity on a stellar scale is squeezing the matter so hard for so long that the strong force itself loses its grip on the individual quarks. There is, as far as anyone can tell, no other place in nature where this particular state of matter exists. Not in the early universe shortly after the Big Bang, where there was indeed quark-gluon plasma, but at much higher temperatures and lower densities than what we are talking about. Not in heavy ion colliders, where the plasma is hot and short-lived. Not in any speculative astrophysical environment that anyone has proposed. The cores of massive neutron stars are on current understanding the unique location in the universe where cold, dense quark matter sits in stable form. If the Helsinki analysis is right, then those inner cores are the only naturally occurring laboratories for this particular kind of physics, and we cannot visit them. We will never visit them. The technology required to send any kind of probe to a neutron star, much less to penetrate its surface and sample its inner core, is not even close to anything humans can imagine engineering. The closest known neutron star is hundreds of light years away. The trip would take longer than human civilization has existed at any plausible spacecraft speeds. Even if we could get there, the surface of the star would destroy any conceivable instrument the moment it made contact. Even if some hypothetical future technology could survive the surface, the inner core sits beneath 10 kilometers of dense matter, with no way for a probe to reach the center without being absorbed and dissolved into the star itself. The matter at the center is by any practical measure permanently inaccessible to us. And yet we know it is there. Or rather, we know that it is most probably there with a probability between 80 and 90%. We have arrived at this knowledge not by going to the matter, but by combining many indirect lines of evidence into a coherent inferential picture. The pulsar masses tell us part of the story. The gravitational wave signatures tell us another part. The QCD calculations tell us a third part. The Bayesian statistical methodology weaves them together into a single quantitative conclusion. We have inferred the existence of a state of matter we will never touch, never see, never test by reasoning carefully from the things we can see and test. This is, in a quiet way, one of the more impressive things our species has done. The slow, patient, multi-generational accumulation of physics, astronomy, and mathematics. From Chandrasekhar's calculations on a ship in 1930, to Burnell's chart paper in 1967, to the Helsinki supercomputer runs in 2023, has built up a picture of the inside of dead stars detailed enough that we can assign probabilities to questions about specific quantum mechanical phases of matter in objects we will never visit. The picture is not complete. The answer is not certain. But the picture is real, and it is converging, and the era when we could only shrug and say, we do not know what, is ending. I want to give you a sense of how strange this connection actually is between what is happening at the center of a neutron star somewhere in the galaxy and what we know about it on Earth. The matter we are talking about is doing something we cannot reproduce. It is sitting in a configuration we have only ever calculated theoretically. It is hidden beneath layers of crust and outer core that block any direct view. It is in stars we have only ever seen as points of light. And yet, with the methods we have developed, we can say that it is there with probability 80 to 90%, and we can describe its general properties with reasonable specificity. If you were trying to explain to a person from any earlier era of human history what science is and what it can do, this would be a useful example. Not the most flashy, not the most dramatic, but a quiet, very deep example of how reasoning under uncertainty, combined with careful observation and careful calculation, can let you say true things about parts of the universe you can never visit. The inner cores of neutron stars on this view are not just a piece of physics. They are a small monument to what patient human inquiry can achieve. Now, there is a complication I want to address, because I think it is honest to acknowledge it. The 80 to 90% figure is a probability, not a certainty. 10 to 20% of the probability mass sits in scenarios where the inner cores of massive neutron stars do not contain quark matter, where the matter remains in a confined state all the way down despite the extreme pressures involved. Some of those scenarios involve different choices about the high-density behavior of QCD. Others involve the matter being primarily hyperons, rather than ordinary nucleons, with the deconfinement transition pushed to higher densities than the cores actually reach. Those alternative scenarios are not zero. They are minority possibilities, but they are not negligible. Future observations might shift the probability one way or the other. The picture might still be revised. So when I say the matter inside is quark matter, what I really mean is the most likely explanation for the matter inside is quark matter. There is a real chance, perhaps 15 to 20%, that the answer turns out to be something else. The honest scientific position is to hold the conclusion with that level of confidence, no more, no less. Holding a probability is itself a different kind of knowing. It is not the certainty of mathematical proof, and not the certainty of direct observation either. What it is instead is the kind of knowing where you have done all the careful work, you have weighed all the evidence, and you have arrived at a quantitative best estimate that you can defend in terms of the underlying methodology. It is the kind of knowing that good science usually produces, especially in domains where direct observation is hard. Most of what we know about the universe, when you look closely at the methodology, is held with this kind of probabilistic confidence, rather than with absolute certainty. That is fine. That is how science actually works. What I want to suggest as we move toward the close of this drift is that the deep interior of a neutron star is one of the more striking examples of the kind of knowledge our species has learned to produce. We have inferred with high but not absolute probability what is happening inside an object that nobody can ever visit, made of matter that nobody can ever sample. The knowledge is real. The probability is not a hand-waving estimate. It is a calculated quantity backed by years of careful work. And the answer, when you let it land, is that the matter inside the cores of the largest dead stars is doing something different from anything else in the visible universe. It is doing the impossible by everyday standards thing that the title of this whole drift was about. The neutrons are dissolving. The quarks are flowing free. The matter is by any reasonable description doing something the rest of nature does not normally do. There is a softness I want to bring into this part of the drift, because the next stretch of the conversation is going to take us toward you, the listener, and toward how this strange, dense matter connects in ways that are physical and not merely metaphorical to your own life. The connection is real. The connection runs through events that happened billions of years ago, when neutron stars in the early Milky Way collided with each other in kilonovae, like GW177, scattering heavy elements across the surrounding interstellar medium. Those heavy elements eventually became part of newer generations of stars and the planets that formed around those stars, and the bodies that arose on at least one of those planets. You contain in the iron of your blood and the trace metals of your tissue atoms that were assembled in events of exactly this kind, in the violent dying of neutron stars long before the Earth existed. But before we get to that connection, I want to leave you with one more image of the matter itself, sitting in its dark home doing its quiet, impossible thing. Imagine a ball of quark fluid, perhaps a few kilometers across, sitting at the center of a neutron star, 800 light years from Earth. The ball has been sitting there for perhaps 100 million years ever since the supernova that created the star. It will continue sitting there for hundreds of millions, perhaps billions of years more, while the star slowly cools and slowly slows its rotation. The matter inside the ball is at densities perhaps 10 or 20 times the density of an atomic nucleus. The temperature in everyday terms is hot, perhaps millions of degrees, but in the quantum mechanical sense relevant to the matter itself, it is cold well below the Fermi energy of the medium. The quarks inside flow as a continuous fluid, neither bound into individual hadrons, nor entirely free in the way they would be in a high-temperature plasma. They are in a peculiar in-between state, made stable by gravity, hidden from view, doing whatever cold, dense quark matter does on a timescale that vastly exceeds the timescale of any human institution, civilization, or species. 800 light years away, doing the impossible calmly, for longer than humans have existed. That is the image I want you to hold, at least in some quiet part of your awareness, as we begin to soften the rest of this drift. The matter is there. We know it is there with high probability. We will not visit it, will not sample it, will not see it directly, but it is there in dozens or hundreds or thousands of neutron stars within reasonable distance of us, in millions of neutron stars across our galaxy, in billions of neutron stars across the visible universe, each one carrying its small, dense, impossible heart, each one in its own quiet way, holding a state of matter that the rest of the universe does not produce in any other place we know. The story from here becomes about you, about how this matter, however hidden, however inaccessible, is connected to your specific life on a specific planet, on a specific evening, when you happen to be listening to a voice describe it. The connection is real. The connection is physical, and it is what we are going to drift toward in the rest of this story. There are about 1 billion of these objects in the Milky Way alone. That is the figure astronomers tend to settle on, give or take a factor of 2, depending on the assumptions when they estimate the total population of neutron stars in our galaxy. 1 billion. Each one a dead star core 12 miles across, weighing more than the Sun, sitting somewhere in the disk or halo of the galaxy, mostly invisible, because most neutron stars are old and quiet and not actively pulsing or accreting. Some of those billion are reasonably close to us. The closest known neutron star, called RX J0740+6620, sits about 400 light years from Earth. There are dozens within 1,000 light years, hundreds within a few thousand. None of them are in any sense a threat to us, because their gravitational reach at those distances is negligible compared to the sun's pull, and their radiation flux at our location is well below anything that could damage Earth's atmosphere or biosphere. They are simply there in the dark going about their slow business, while our planet does its own slow business much closer to home. If the Helsinki result is correct, then a substantial fraction of those neutron stars, particularly the more massive ones, contain quark-matter cores. Not all of them. The lower mass neutron stars around 1 4/10 solar masses probably do not reach the densities required for deconfinement, but the heavier ones, the ones near 2 solar masses, very probably do. We are talking about plausibly hundreds of millions of objects in our galaxy, each containing a region of quark matter at its very center. Hundreds of millions of small, impossible hearts, each one tucked away inside a city-sized sphere of crust, an outer core hidden from any direct observation, doing the strange physics that the equations have always predicted, but that no laboratory has ever reproduced in stable form. This is the picture. This is what the science has converged on in the last 5 years, after 40 years of theoretical work and decades of patient observational accumulation. The dead cores of dead stars scattered throughout our galaxy in vast numbers contain at their heart a state of matter that exists nowhere else we know about. The matter is real. It has been there in some of those stars for hundreds of millions of years. It will continue to be there while the rest of cosmic history unfolds around it. While our planet continues its orbit around our star, while our species continues whatever it is going to continue doing on the surface of our small, warm world. I find this picture, when I let it settle, to be one of the more quietly remarkable things I know about the universe we live in. Not because it is dramatic in any grand sense, not because it changes anything practical about life on Earth, because of what it says about the relationship between the universe and us. We are small. The neutron stars are small too, by cosmic standards, mere city-sized leftovers from the deaths of more substantial stars. But the universe has at the centers of those small dead objects hidden a state of matter that exists nowhere else, that we cannot reach, that we cannot reproduce, and yet that we have been able to figure out is there with a quantitatively defensible probability by careful observation from a great distance. That is, in some quiet sense, the kind of relationship our species has with most of the cosmos. The interesting things are far away. The interesting things are not things we can visit or sample. The interesting things are things we have to reason about carefully from the small fraction of evidence that reaches us using the principles we have learned and the tools we have built. And against expectation, against the apparent unreachability of so much of what is out there, we keep managing to figure things out. Slowly, patiently, with many false starts and many revisions, but cumulatively over generations, a picture of the universe takes shape, and parts of that picture become detailed enough to assign probabilities to specific physical questions about specific kinds of matter sitting in specific kinds of objects. Tonight, in the quiet of wherever you are sharing a galaxy with hundreds of millions of small, dense, impossible hearts. They are not aware of you. They have no way to be aware of you. They are not waiting for you. They are not asking anything of you. They are simply there in the dark doing the physics they have always done. Some of them are spinning rapidly enough to send their lighthouse beams across the galaxy hundreds of times per second. Some of them are quiet, having long since cooled and slowed down. Some of them are in close binary systems, slowly being eaten by companion stars glowing in X-rays as the matter falls onto their surfaces. Some of them are heading toward eventual mergers with their partners on timescales of millions or billions of years. All of them, the massive ones, at least very probably contain at their cores the kind of impossible matter we have been talking about all night. You and that matter share a universe. You will never visit it. You do not need to. The fact of it being there, the fact of our species having figured out that it is there, is its own quiet wonder. The quark fluids in the cores of the most massive nearby neutron stars have been sitting in their dark homes for longer than any human civilization has existed. They have will outlast anything our species has ever built or will ever build. They are part of the long, slow furniture of the galaxy, doing what they do, regardless of whether anyone notices. We have noticed. That is the thing I want to leave you with as we move into the warmer part of this drift. We are a species on a small planet. We have figured out against all the apparent odds that the matter in the cores of the dead stars across our galaxy includes a phase that the rest of the universe does not produce stably anywhere else. We have figured this out without ever leaving our own atmosphere. We have figured this out from the patterns in the radio waves and X-rays and gravitational waves that arrive at our small terrestrial detectors after traveling for thousands of years from the distant objects whose physics we are trying to reconstruct. It is by any reasonable measure an act of attention. The universe does not require us to pay attention to it. The neutron stars certainly do not. But our species has, over the course of about 100 years, built up the tools and the methods to know what is happening at the centers of these objects with quantitative confidence. The result, when it lands, is a kind of quiet intimacy with parts of the universe that no human will ever physically reach. The work is not done, of course. The Helsinki paper is the strongest single statement to date, but it is not the final word. New observations keep arriving. NASA continues to measure the radii of nearby pulsars from its perch on the International Space Station. LIGO and Virgo, joined more recently by Japan's Kagra detector, continue to look for new gravitational wave events from neutron-star mergers, with each detection adding another data point to the equation of state constraints. Radio telescope arrays around the world continue to time the most precise pulsars to fractions of a microsecond, looking for the subtle signatures of orbital companions and gravitational interactions that further constrain the masses involved. The square-kilometre array currently under construction across South Africa and Australia will, when complete, provide pulsar timing data of a quality that exceeds anything currently available. Each new observation, when it arrives, gets fed into the same kind of Bayesian inference machinery that the Helsinki team used. The probability of quark-matter cores might rise as new evidence converges on the high-density regime. It might fall if some new observation reveals something unexpected about the matter inside neutron stars. The methodology is now in place. The current best estimate is between 80 and 90%. The estimate will get refined year by year as the data continues to accumulate. We are watching in real time one of the deeper open questions in dense matter physics moving slowly toward a clearer answer. Through the patient combination of theory and observation that is the actual texture of how science usually works. There is a difference between the kind of intimacy you have with the people you love and the kind of intimacy you can have with cosmic phenomena. The first kind is two-way. The second kind is not. The neutron stars do not love us back. They do not respond to our interest. They do not adjust their behavior because we are watching. Whatever connection exists between us and them is entirely on our side. We do the watching, they do the existing. The connection consists on our end of careful, patient understanding. But the connection is real. And tonight, with everything we have just walked through, you are part of it. You are part of the species that has done this work. You are part of the small and recent set of beings on this small and recent planet who have arrived at the picture of dense matter that the Helsinki paper crystallized. The picture exists in your own mind, at least roughly after the last few hours of drift. The neutron stars in our galaxy continue doing what they do, indifferent to your awareness. But your awareness exists, and it includes, however vaguely, a sense of what is at the bottom of those objects, and that sense is whatever else it is, an act of human attention paid to the rest of the cosmos. So let us soften from here. The technical picture is in place, the probability is on the table, and the matter is there at the bottom of the dead stars, doing its impossible physics in the dark. What remains is for the story to come back to you, to your specific life on your specific planet, and to the connections that run between the neutron stars and the world around you in ways that are physical and ancient, and quietly continuous with everything we have just been through. There is iron in your blood. You probably already knew that. The hemoglobin in your red blood cells is built around iron atoms, which is what gives the cells their ability to bind oxygen and carry it from your lungs to every other tissue in your body. The iron is essential. Without it, you could not breathe in any meaningful way. Each adult human body contains roughly 4 grams of iron distributed across the blood, the muscles, the liver, and various enzymes throughout the body. It is one of the more significant elemental components of you, alongside carbon and oxygen and nitrogen and hydrogen and a few others. Some of those iron atoms, the ones in your hemoglobin tonight, were assembled in the cores of stars that lived and died before the Sun and the Earth ever existed. The basic elemental nuclei of iron are produced primarily in massive stars near the end of their lives, in the brief stretch of nuclear burning that happens in the days before a supernova explosion. The supernova then scatters the iron across the surrounding interstellar medium, where it eventually finds its way into new generations of stars, planets, and on at least one planet, into living bodies. Most of the iron in your blood was made in some massive star a long time ago, in a process we understand reasonably well in places throughout our galaxy where stars happen to be lying when their lives ended. But there are other elements in your body that were not made in supernovae. The trace amounts of platinum and gold and a handful of other heavy elements in your tissues, the small fraction of strontium in your bones, the tiny pieces of various other heavy metals scattered across the chemistry of your cells, were made in events more violent than any individual supernova. They were made in collisions between neutron stars, in events like the GW0740+6620 merger that LIGO detected in August of 2017, in kilonovae. The reason has to do with the specific physics of how heavy elements are built. Most elements lighter than iron are made by fusing lighter nuclei together in the cores of stars. The fusion process releases energy. It is exothermic. Stars do this routinely throughout their lives, and the elements lighter than iron get distributed across the universe through stellar winds and supernovae. But making elements heavier than iron is different. Fusing nuclei beyond iron costs energy, rather than releasing it, so it does not happen spontaneously inside ordinary stars. To make heavy elements, you need an environment with extremely high neutron flux, where neutrons are flooding the existing nuclei faster than the nuclei can decay back to lighter forms. The rapid neutron capture process, called the R process, is what physicists call this. And the R process requires conditions much more extreme than what you find inside an ordinary supernova. For decades, the question of where the R process actually occurs in the universe was debated. Some kinds of supernova were thought to be capable of producing the conditions. Other proposals involved more exotic environments. The 2017 GW0740+6620 merger settled much of the debate. The kilonova that followed the gravitational wave signal showed clear spectroscopic signatures of R-process elements being produced in real time in the debris cloud of the colliding neutron stars. The collision had stripped vast amounts of neutron-rich matter from the two stars, hurled it into the surrounding space, and provided exactly the conditions needed for the rapid neutron capture process to proceed. Heavy elements like gold and platinum and uranium were synthesized in the debris, along with hundreds of other rare and exotic isotopes, and then scattered across the interstellar neighborhood of the merger. Events like that have been happening in our galaxy for billions of years. Every time two neutron stars in a binary system spiraled into each other, every time a kilonova went off, the resulting cloud of heavy elements eventually mixed into the surrounding gas, found its way into new star-forming regions, and ended up incorporated into new generations of stars and planets. Earth was formed from one of those gas clouds 4.5 billion years ago. The cloud already contained heavy elements from many previous generations of supernovae and kilonovae. Those elements ended up in the rocks and the oceans, and eventually in the bodies that began to grow on Earth's surface. So when I say that you contain elements made in kilonovae, this is not a metaphor. It is a description of how the periodic table actually got distributed across the chemistry of your body. The gold in any wedding ring you might be wearing if you have one, the trace platinum in some of your enzymes, the tiny amounts of various other heavy elements that show up in spectroscopic analyses of human tissue. Most of those atoms are statistically the products of ancient neutron-star collisions scattered across the proto-Milky Way before the Sun was born, swept up into the cloud that became our solar system, and incorporated into the chemistry of your cells through the long downward chain that runs from interstellar gas to planet to ocean to organism to you. This is the connection I want to leave you with as we move towards sleep. The matter inside neutron stars is not separate from you. It is not abstract. It is not just out there in the dark doing its strange thing in objects you will never visit. The dead stars, whose cores we have been descending into all night with their iron crusts and their nuclear pasta, and their superfluid neutrons and their probable quark-matter cores, are part of the chain of physical processes that produced you. Earlier neutron stars billions of years ago in the same galaxy you live in collided with each other and threw heavy elements into the interstellar medium. Those elements are inside your body right now. Your body, in some real and physical sense, is partly made of the debris of ancient neutron star deaths. You are connected to these objects, not by interest, not by attention, but physically through the atoms in you, through the chain of cosmic events that brought those atoms here, through the long story of stellar life and death that has been running in our galaxy for most of cosmic history. I want you to feel that connection as gently as you can before we wind down. Wherever you are tonight, however close to sleep you are getting, the iron in your blood is moving. Your heart is pumping it through your circulatory system at the steady rate it has maintained since before you were born. The hemoglobin in those iron atoms is binding oxygen in your lungs and releasing it in your tissues in a quiet rhythm you do not have to think about. The trace metals in your enzymes are doing their slow chemical work, helping the cellular machinery turn over, helping the long maintenance of your living body proceed. All of this matter, all of these atoms came from somewhere. The hydrogen mostly from the early universe shortly after the Big Bang. The carbon and oxygen and nitrogen mostly from the cores of earlier generations of stars. The iron mostly from the explosive shells of dying massive stars. The heavy elements gold and platinum, and the rest mostly from the kilonovae of ancient neutron star collisions. You are in a real sense a temporary arrangement of cosmic material. The arrangement is yours. The material is older than the Earth. There is something quieting about this when you let it land. You are not separate from the universe. You are not visiting it temporarily. You are part of it, made of it, woven into it through the slow chain of nuclear and chemical and biological processes that have been running since long before any conscious being on Earth could think about them. The neutron stars in our galaxy with their probable quark-matter cores are part of the same continuous physical reality that you are part of. They are not far away in any deep sense. They are just operating on a scale and at a depth that puts them out of reach of any direct human contact. But the connection through the elements is real. The connection through physics is real. The connection through the long history of cosmic evolution is real. You can rest in that connection. You do not have to do anything with it. You do not have to perform any feat of imagination or any leap of insight to participate in it. Your body is participating in it right now through the simple ongoing fact of being alive on a planet whose chemistry is what it is. The iron pumping through your circulation, the trace metals in your tissues, the various heavy elements that show up in any careful chemical analysis of your body are all there doing their work regardless of whether you are paying attention to them tonight. Let yourself rest. The neutron stars do not need you to be awake. The matter inside them, with its high probability of being quark fluid, will continue doing what it does whether you stay conscious or fall asleep. The iron in your blood will continue moving whether you focus on it or not. The whole vast physical setup of which you are a small but real part will continue running gently while you go where the night takes you. The dead stars are out there. The hundreds of millions of small, impossible hearts in our galaxy are sitting in their dark homes doing their cold, dense quark-matter physics on timescales that stretch across most of the age of the cosmos. They have been there since before life appeared on Earth. They will be there long after our species and our planet are gone. The matter inside them is by the best current calculation doing something the rest of the universe does not produce in any other place. And the elements that came from earlier objects of the same kind are right now inside you, doing their quiet, ongoing biological work. There is a simple sense in which you and a neutron star are both part of the same universe doing different things. The neutron star is doing the most extreme thing the universe knows how to do with matter and gravity. You are doing one of the most subtle things the universe knows how to do with matter and chemistry. Both processes are real. Both processes are continuous with each other through the long chain of cosmic history. Both processes are happening right now somewhere in the same galaxy that contains both of you. I think there is something in this picture that is genuinely worth carrying with you beyond tonight. Most of us, when we think about the cosmos in any serious way, end up with a sense of how small we are compared to it. The universe is vast, the timescales are deep, the distances are unbridgeable, and our own lives are short and local and seemingly insignificant against that backdrop. That sense, when you let it dominate, can become a kind of cosmic loneliness, a feeling that we are stranded on a small planet with no real connection to the larger reality around us. But the connection is real. The atoms in your body have been here in this universe for almost all of cosmic history. The hydrogen was made shortly after the Big Bang. The carbon and oxygen were made in earlier generations of stars. The iron came from supernovae. The heavy elements came from kilonovae of merging neutron stars. Each of those atoms has its own long history, its own slow journey through the chemistry of the cosmos before ending up in the specific arrangement that is currently you. You are not separate from any of it. You are made of it. The same universe that produced the impossible matter at the bottom of the dead stars produced eventually the temporary arrangement of older atoms that is sitting in your specific room tonight listening to a voice describe the dead stars. The connection works in the other direction too. The neutron stars with their probable quark-matter cores are the products of the same cosmic processes that produced you. They came from massive stars that lived and died. Those massive stars in turn were made from gas that had been enriched by previous generations of stellar deaths. The whole chain runs continuously from the early universe through generations of stars and their endings to the present moment, with neutron stars and human bodies both as recent expressions of the same long physical process. We are not separate phenomena. We are different shapes. The same matter takes on different scales in different conditions, governed by the same underlying physics. Let the connection be enough. Let it be quietly true without requiring anything more from you. The matter at the centers of the dead stars is there doing its impossible work. The matter in your body is here doing its ordinary work. The two are linked through the slow generational chain of stellar deaths and rebirths that has produced both. You can sleep on that. You can let the world soften while the universe continues with you in it, with the neutron stars in it, with all of it carrying on its long, quiet business through the night. You belong here. You always have. The matter you are made of has been part of this universe for billions of years. Your specific arrangement of that matter, the particular pattern that is you, is recent and brief. But the matter itself, the underlying stuff, is old and continuous and woven into the same fabric that holds the neutron stars and their impossible cores. You are not an interloper in the cosmos. You are an expression of it. The same physics that produced the dense matter in the dead stars produced eventually you listening tonight, breathing slowly, getting closer to sleep. Let the voice begin to fade. Let the matter in your body continue its ordinary work without your supervision. Let the neutron stars in our galaxy continue their dark, dense business without your attention. Let yourself rest here in the warm, specific room you happen to be in, while the cosmos that contains both you and the impossible matter you've been hearing about continues quietly, indifferently, and entirely without need of your wakefulness. We have come a long way tonight, from the surface of a small dead star sitting in the dark 12 miles across, weighing more than the sun, all the way down through every layer to the impossible matter at the very bottom. We met the people who first predicted these objects in 1934. We met James Chadwick discovering the neutron in 1932, and Subramanian Chandrasekhar working out the maximum mass of white dwarfs in 1930, and Walter Baade and Fritz Zwicky proposing the existence of neutron stars 2 years later, and J. Robert Oppenheimer and George Volkoff writing down the upper mass limit in 1939, and Jocelyn Bell Burnell finding the first pulsar in 1967, and dealing with the little green men joke that nearly ended up in the literature. We walked through the crust with its iron lattice and its nuclear pasta. We walked through the outer core with its superfluid neutrons and superconducting protons and its degeneracy pressure holding everything up against gravity. We arrived at the inner core with its long-standing puzzle about what the matter is doing at the deepest densities. And we landed finally at the December 2023 paper from Alexei Vuorinen and Jonas Nattila and Jonas Hirvonen and their colleagues at Helsinki with their Bayesian methodology and their millions of CPU hours at the CSC Supercomputer Center, and their answer of 80 to 90% probability that the matter at the bottom of massive neutron stars is in a deconfined quark-matter phase. That is the technical picture. That is the science. What we sat with after that in the resolution was the connection between those distant, impossible hearts and your own ordinary body, the iron in your blood, the trace metals in your tissues, the heavy elements in any wedding ring or piece of jewelry you might be wearing. Most of those atoms were forged in events very much like the G0740+6620 merger that LIGO detected in August of 2017. Earlier neutron-star collisions billions of years ago in the proto-Milky Way scattered the heavy elements across the interstellar medium, and those elements eventually ended up here in you, in your circulatory system, in the chemistry of your cells. The matter inside neutron stars and the matter inside you are not separate domains. They are part of the same continuous physical universe connected through the long chain of stellar life and death that has been running in our galaxy for most of cosmic history. If you want to hold one piece of the story as you fall asleep, let it be that the dead stars are not separate from you. The matter inside them, however, hidden, however inaccessible, is part of the same physics that produced you. Hundreds of millions of small, impossible hearts scattered through the Milky Way, connected by the long generational thread of stellar evolution to the iron in your blood and the platinum in any small piece of jewelry you have. That is the picture. That is the connection that runs underneath all the technical detail we have been through tonight. Before we let this drift end, I want to thank you for being here. Cosmic Drift is a small project made for evenings exactly like this one for people who want a quiet voice and a slow piece of cosmic science to carry them towards sleep. Every person who listens, who stays through the long stretch of the technical material, who lets the slow descent through the layers of a neutron star become part of their settling into rest, is what makes this channel possible. If you have enjoyed tonight's drift, the gentlest thing you can do is hit the like button and subscribe to the channel. It is a small gesture. It costs you nothing, but it tells the recommendation algorithms that this kind of slow, patient space documentary is worth recommending to other people who might need it. We are not asking for anything more than that. If you have already subscribed, thank you genuinely. That means more than you might realize. And now, as we close, I want to leave you with one last image. Somewhere in our galaxy tonight, perhaps 400 light years from your specific room, perhaps a few thousand light years away, perhaps tens of thousands of light years across the disk of the Milky Way, there are dead stars sitting quietly in the dark. Some of them, the most massive ones, contain at their cores a region of cold, dense quark fluid, doing the strange physics that the equations have always predicted, but that no laboratory has ever reproduced. The fluid has been there in some of those stars for hundreds of millions of years. It will continue to be there doing its patient, impossible work, while the rest of cosmic history unfolds around it. You will not visit it. We will not bring it home. The matter at the bottom of those dead stars is by any practical measure permanently out of reach, but it is there. Real, calculated and backed by the careful work of a research group in Finland and many other groups around the world, all converging on a picture that the field has been chasing for decades. The matter is doing what the equations say it should do in the place where the equations say it should be in numbers that probably reach into the hundreds of millions across the galaxy. The dead stars are spinning slowly. The crusts are quiet. The outer cores are flowing in their superfluid way. The inner cores are doing whatever cold quark matter does. And you here in your room in this specific moment are part of the same universe that contains all of them. Sleep well. The dead stars will keep the impossible matter, will keep the long quiet physics of the cosmos, will keep going through the night. The voice is fading now. The drift is ending. Thank you for letting us carry you through one of the strangest and most patient stories the universe has on offer. The matter is there 400 light years away, or 4,000 or 4 million, doing its silent, dense, impossible thing in the dark. The galaxy turns slowly around it. You rest here in your warm, specific room, part of all of it. Good night.